Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to continue talking about uh, integrals. We did the line integral before, and today we are going to introduce the surface integral. And or today, I'm going to deal with the surface integral in a scalar field. And then next session, we'll do the vector field. So, what is that surface integral? Remember that when you take a double integral in a plane, like, you know, x and y, and you take a double integral, you have a plane. So we know how to do that. But what if when we have an xy function, or in fact, x, y, and z in a curved plane, a curved one? So we are in 3D now. So we have something that maybe it looks something like that. So this is a surface, and if I take any point here, I can parameterize the surface by creating two directions, u and v, right? Now we learned that in math, when we dealt with vectors, we learned something called the cross product of vectors. When I do a cross product of vectors, I get a result is a third vector perpendicular to the plane. So at this point, it's like I'm drawing a line perpendicular to that plane. Okay? Now, but that's not the big issue. The big issue is that the magnitude of u cross v equals the area of the parallelogram formed by crossing u and v. So if I draw a line parallel to u, a line parallel to v, it gives me this area. Meaning, if I take the integral of the whole thing and then multiply it by f, it will give me the surface integral I'm looking for. So the way we do it, we are going to write the function. My function probably is f of x, y, and z, right? I'm going to parameterize it and make it a function of u and v. Then I'm going to find um, the derivative. So um, I want to get the tangent to the surface in the u direction, which is partial f partial u, and get a tangent in the v direction, which is f partial v, cross them out, get the magnitude, multiply by the field, the force itself, which is the field, not the force, a field, times that, and take the integral over the surface du dv. So that's in a nutshell what we are going to do. First, we are going to parameterize the function. Then we are going to find the tangents in two directions that we call u and v. Take the partial derivative with respect to u and v, that's basically the tangent, cross them out because that would give me this area, multiply by the field, which is a scalar on top of the surface, and take the integral du dv. Let's take an example and see how it's done. So we are going to start with an example today that we want to evaluate a function which is just y, okay, over a surface, and this surface is given by z equals x plus y squared, where x goes from 0 to 1 and y goes from 0 to... I can work with x, y, and z, well, but usually if you want to parameterize, it's so easy now because you have you want to take only x and y, and you already have z expressed as a function of x and y. So we can say I don't like to do that. I just use x, y, and then z. But we can say let u equals x v equals y. So z in this case would be x plus v squared, right? And then my u goes from 0 to 1, and my v goes from 0 to 2. So that was easy, a step that I can just ignore and work with x, y, and z. Oh, I'm sorry. I should say u here, not x. Yeah, I was going to write x plus y squared, and then that doesn't make any sense. So you can see I could have I stayed with x, y, and z. Next step, I want to find partial f or partial u, because now when I write this, I get partial, or let's call it f sub u. Partial u would be in the x direction, the derivative with respect to u is 1. So 1 or I, 1i or I. In the This y doesn't have u, so plus 0j, right? And then for the k, I have u, so plus k or 1k. F with respect to v. So if I take the partial with respect to v, there is 0i, just 1j, so plus j. But I have 2v in the k direction. Now we do, next step, as we said, we are going to do the cross product of cross fv. Like we did before, I, j, k, 1, 0, 1, 0, 1, 2v. So in the I direction, I get 0 minus 1, so negative I. In the j direction, we do it backwards. So this is 0 minus 2vj. And then in the k direction, I get 1, so plus k. Next step is to find the magnitude of fu cross fv. It's the square root of negative 1 square plus negative 2v square plus 1 square. So it's the square root of 2 plus 4v square. Finally, you are going to take the integral after you multiply f. F in this case is just y. So, and y is v. So I'm going to say, take the double integral. U goes from 0 to 1 and v goes from 0 to 2 of y, which is v, times the square root of 2 plus 4v squared du dv. Notice u and v are not related, so I can do the integral of du. So this is as if I have the integral from 0 to 1 of du times the integral from 0 to 2 of v times the square root of 2 plus 4v squared dv. When you integrate that, you get u evaluated from 0 to 1, so that's 1. Okay? So really, that's 1. So basically, I have to integrate that. You can see that if I had 8v outside, well, it's easier for some of you to use just substitution. So let's say, I'm not going to use u and v because that would be, of course, or x and y. So I'm going to say, let t, for example, equals 2 plus 4v squared. So dt equals 8v dv. And now I'm going to write back in terms of t. So I have v dv, meaning dt over 8. So it's the integral, 1/8. So I already took v and dv, divide them by 8 to get dt. And what's inside the radical? was t. As we said multiple times, you can change the limits of integration. Don't please use 0 and 2. If you are going to stay in the t universe, then you have to say, okay, when v was 0, t was 2, so you take the integral from 2, and when v was, I'm sorry, yeah, when v was 2, this is 4 times 4 is 16 plus 2 is 18. So you can take the integral from 0 to 2. I'm sorry, from 2 to 18. Or, or you can leave it as if it were an indefinite integral, and when you get your result, you go back to the v word and evaluate from 0 to 2. It's the same thing, okay? So usually I go back, so this time, let's say when v equals 0, t equals 0 squared times 4 is 0 plus 2 is 2. So the lower is 2. And we said when v equals 2, 2 squared is 4 times 4 is 16 plus 2 is 18. And you can do it like that. Now, this is so simple. It's t to the 1/2. So when you evaluate the integral, you get t to the 3/2 divided by 3/2, meaning multiplied by 2/3. And the t is evaluated from 2 to 18. Now, the 2 and the 8 would make that 4. So this is 1 over 12, 18 to the 3/2 minus 2 to the 3/2. Okay? So it's 1 over 12. The 18 to the 3/2, notice 18 is 9 times 2, right? So I can write it 9 to the 3/2 times 2 to the 3/2 minus 2 to the 3/2. 9 to the 3/2, if you take the square root of 9, you get 3. Cube is 27. So you get 1 over 12. 27 times 2 to the 3/2 minus 2 to the 3/2. You factor out 2 to the 3/2 over 12 times 26, right? 27 minus 1 when you do that. But what is 2 to the 3/2? It's 2 root 2. So this is 2 root 2 times 26 over 12. You simplify the 2 with the 2, you get 6. You simplify the 26 with the 6, you get 13 over 3. Oh, I'm sorry. I simplify by 2. And yeah, 2 I divide by 4, right? So I get 13 root 2 over 3. This is the first example. Okay? Now, let's take another example. The second example, give me a function, still scalar, but its magnitude is x plus y plus z. And they give me the surface already parametrized. It's R of u and v. And again, u from 0 to 2 this time, and v from 0 to 1. So the first thing we do, since we already have everything, is to take Ru, meaning the derivative, partial derivative of R with respect to u. So I get I, u again, so plus j, and 2u plus 2k. And when I take the derivative, partial derivative with respect to v, I get also I get minus v plus k. So now the Ru cross Rv would give me I, j, k, 1, 1, 2, 1, negative 1, 1. Which yields, in the I direction, I get 1 minus negative 2, or 1 plus 2 is 3i. In the j direction, I get 2 minus 1, so plus j. In the k direction, I get negative 1 minus 1 is negative 2k. Finally, the magnitude of RU cross RV would give me the square root of 9 plus 1 plus 4. 3 square plus 1 square plus negative 2 square. Until now, I still see students say minus 4. No, the square is always positive. These will always be added. Something similar to what you do in when you calculate the variance. You never subtract, even if the combination has negative signs. And this is square root of 14. Oh, that's a constant, right? So it's just square root of 14. Now, I have uv, uh, so I have x plus y plus z. And I think in this problem, they give us the, oh, did I write the relationship in the surface? Yeah, this is x, so f of u and v is x u plus v plus y plus u minus v plus z plus 1 plus 2u plus v equals v minus v cancel. So I get 4u plus v plus 1. And now I take the integral, double integral of u going from 0 to 2 and v from 0 to 1. Root 14 is outside, it's a constant. 4u plus v plus 1 du dv. So when I take the integral with respect to u first, I will get 4u, the u becomes u square over 2, the 4 over 2 is 2, so you get 2u square plus uv plus u evaluated from 0 to 2 dv. The u is evaluated like that, so I get root 14, integral from 0 to 1, and between parentheses, when this is 2, you get 8 plus 2v plus 2 dv equals root 14, integral from 0 to 1 of 2v plus 10 dv equals root 14 v squared plus 10v. When you integrate, evaluate it from 0 to 1, again, we don't care about the 0, so you get 1 plus 10 is 11, so the answer is 11 root 14. And that is the surface integral. I hope that was simple enough. If you have any questions, you can always send me a comment in the comment sections. Otherwise, I wish you all the best. I hope to see you next when we do the vector field. So surface integrals in vector field. Thank you very much.